Introduction to vectors. So in this particular video, what we're going to talk about is kind of the difference between scalars and vectors, to introduce you back into that. You maybe have seen this in physics, okay, maybe even in calculus at some particular point. I hope so. So that would be one item. I'll talk about kind of the various notations for vectors. So sometimes, we refer to them as geometric vectors when we start plotting them out, especially in the beginning, as you kind of see them in 2 dimensions, and then you can take them to 3 dimensions. Unfortunately, as you go into further dimensions, it's not very easy to be able to visualize. I certainly am not capable of doing that if I go into a little bit further than the 3 dimensions. So you'll see those notations in here. So I'll talk about kind of magnitude, how you can express the direction of a vector. You can utilize kind of true bearing or azimuth bearings, okay, with respect to north. You can also utilize the quadrant bearing when you start talking about north, south, west, and east. And then you can also do it by regular standard degree reference, okay, with respect to the horizontal, which is equal to 0, and you're probably very familiar with that from just the basic quadrants of a Cartesian plane. So that's how you can do that, at least in 2 dimensions. Now, you should be able to kind of convert between those different bearings, different representations of directions, if you ever were asked to. I don't think it's super difficult. Once you see 1 or 2 examples, you typically are fine. And then the last thing that we'll talk about is kind of parallel vectors, equivalent vectors, and then vectors that are opposite to each other. So basically just in different directions. So that will be the introduction to vectors in this video. So the first concept that I want to discuss is actually this concept of scalars versus vectors. Now, there was, a video that I've done before, and it was in particular for scalars and vectors, introduction to kind of displacements and, speeds, velocities, acceleration. So that is something that you might have touched on. I'll put up a link up above there with respect to that, especially for any student who has a little bit of a familiarity with calculus, okay? So you can see that. If you've done this in physics, you maybe will be doing it from the viewpoint of various quantities, which is exactly what I like to do. I do have a little bit of a physics engineering background, so I love covering these scalars and vectors with respect to quantities that we see kind of in everyday basis. So here is a little bit of a chart. I'm going to kind of scroll back down here. Okay, and there's various quantities that you 100% have run into. Now, there's many more, but these are kind of the more familiar ones. So now I want to be able to distinguish for you kind of the scalars and vectors, and then what we really want to think about. So scalars in general is just some kind of a measurement that does not have any direction at all. Now, so if you're thinking about, directions, what do you mean by a direction? Well, if you're moving, okay, especially if you're kind of going from one place to another, it's kind of the easiest way to think about, well, my direction at the end, maybe I'm heading towards the subway, maybe I'm heading towards my car, maybe I'm heading towards the mall. And then you can start giving various directions, with respect to the position that you are moving along with. Now, if you just wanted to know what the distance is that you cover, okay, between one point and another, or on the path that you're going. So for example, in here, you wouldn't really care much about what the direction you went. You would just say, okay, how much distance did I cover? Maybe I went 100 meters, maybe I went, 340 meters, or whatever that distance might be. So we would actually think, okay, and typically we do think in terms of distances as just simply scalars, because they don't really think about direction per se. Now, of course, it depends how you can define them, okay, because you can have a particular distance, okay, that you're going, and maybe you do want to think about a direction. So, if I would plot this out, okay, a kind of a nice path in here. So let's say I'm starting from right here, and then I'm moving, in this particular direction, and then eventually I end up somewhere over here. Okay, so this is my starting point A, and then this is my finish point B. So I could have covered a certain amount of distance. Let's just imagine that maybe this was, 250 meters. okay, as you glazed through, okay, this entire path, okay, as you were going along, you know, on this path, and, you know, so you went all the way over here, you know, you kept following through, okay, and then you eventually ended up somewhere over here. So that would be the distance that you covered, and that's just simply a scalar. Now, at any single point that you're moving along, you can have a position which could be a vector, right? So you could, for example, say that, well, maybe I'm referring to that at this particular position, you know, maybe I'm moving in this direction, okay? So I'm moving kind of upwards, maybe that's north, okay? And if you would say that, you know, that would be an actual direction that you have. Now, that would be in terms of the direction, would be just in terms of the position. And now, of course, you can have that position at any point. You can say, okay, over here, maybe I'm moving somewhere in that direction. Okay, and then over here, you know, I'm moving in a particular direction right here. So I think students in general kind of do sense an idea of a direction. You know, you can think of directions north, south, north, northeast, or whatever it might be. Okay, so those are the direction that we can be heading in. Now, we also have a very kind of convenient way that maybe we're only interested in going from one point to another, and we wanted to be able to figure out, you know, what is the total, okay, distance that we covered, okay, from this point to this point, but not necessarily along that path. But if we take the shortest path, okay, from one point to another, so if I take this particular path, if I walked all the way through, now of course there would be no buildings or nothing like that, I can actually go straight across. Well, this would be referred to not as a distance, but this would have been actually a displacement. So it is the displacement, okay, that you would actually cover. And displacements are vectors. So, you know, we do think of them as actual vectors because we want to be able to go from point A to point B, okay? So we've went through these particular directions, but, and this is where we do this little kind of a sign, okay, between one point and another, and we put this little arrow right on top, okay, and we basically say that, hey, this is actually a vector. It also involves, okay, an actual direction. So I can calculate what this distance is, right? So from A to B, I can figure out exactly what that distance is. But that particular distance would just be the magnitude, right? So from A to B. Now you can see that it's going to be the shortest path. So that means it's going to be less than the actual distance that I covered along there. But it also will have a direction. And in this case, you know, maybe the direction in here is, if this was, you know, let's say maybe north over here, okay, and then this is east over here. So, you know, maybe this is the direction, okay, that I've headed northeast, okay. So within here, so this displacement, and displacement we actually do utilize in physics, okay, we utilize the letter, okay, or the actual variable s, okay, so that we have, and if we want to be able to say exactly, okay, that it is a vector, you know, we can say that. Now, I don't know what that actual distance might be. Let's say maybe just for convenience, let's, you know, say that it was a 100 meters, but we're now adding a direction and it was northeast. So as soon as you have this, okay, plus your actual direction, then you're making it a vector. And that is now where you're going to be heading. So this introduction to these vectors, okay, because we do want to know kind of not only the actual magnitudes that we cover, but we also may want to know what the direction that we are heading in. And that would be important. You know, if you're flying, you don't want to just know what the distance you covered. You actually are kind of thinking what direction you're going to be heading. If you're going to be driving, you do the same thing, right? If you want to get to a certain location, it's not just the distance that you're covering that's important to you. It's also, you know, whichever direction that you're heading. Okay, and then from that point A to point B, that would be the total displacement that you had. Okay, so that is something that you can think about. Now, there are many other quantities. Now, with distance, obviously, you can talk about things like speed, right? So speed is actually technically a scalar. It is, you know, how quickly am I moving? You don't really care which direction you're heading. So when you're looking at the speedometer, you're actually just reading the instantaneous speed. It doesn't really necessarily tell you what direction. Now, the cars nowadays might have a direction associated with it, but as soon as you add a direction to the actual speed, then you're talking about a velocity. So velocities are typically known as actual vectors. And in terms of the notation for them, so for speed, okay, you typically would still write, for example, in physics, we might still write v, but if we want to be very specific, this would be a small v, we would put a directional, okay, kind of a vector on top of it. So this would have been the actual scalar that you would have, and this would have been a vector. Now, the unfortunate part is that as you're doing this, sometimes people drop this. They don't always put this, and then you're not sure if it's a vector or scalar. Yes, as mathematicians, as physicists, scientists, we do get sometimes lazy and our notation drops off. But if you want to be very specific and tell somebody, you put that little arrow right on top, and then you can say that, okay, so this is an actual vector measurement. So it's a quantity which will have a measurement with a scalar, the magnitude, plus the direction that it will be heading in. Sometimes those directions are useful, right? Sometimes they're not so useful. We may not always kind of think about them in terms of things that we might need. Now, if you're looking at these, so for instance, there's quantities that don't necessarily have a vector, okay, associated. So for example, the second one, as you see there, the mass actually just measures how much matter you're made up of, right? Or whatever object is, okay? So how much matter is that made up of? That's not a vector. That's just a scalar quantity. And that scalar quantity will have a measurement, but there's not going to be a direction. Now, you can talk about time, okay? So time as well doesn't really have a direction. It just kind of passes by. So it's also known as a scalar quantity. Temperature that you're reading, right? So temperature is really, how quickly atoms are moving in the air, okay? And we want to, or not necessarily in a gas like air. It could be a liquid, it could be a solid. But, how are those actual atoms vibrating or moving around? Okay, that's what temperature actually is. It's kind of a measure of, how much heat that there is, okay, or energy within those. And that is just simply a scalar. We just want to be able to measure it. And there are many others that are mostly just scalars. As you look at this list, okay, and as you kind of head along in here, you'd say, well, mass is really just a scalar. Time is kind of a scalar. Temperature is a scalar. The amount of substance that you have, so notice that in here, it's a measure in moles. So this is a little bit of chemistry. Well, that's also a scalar. It doesn't have a direction. It's kind of pointless. Number of something as you're counting things up. I don't know, maybe, I'm going to be counting, okay, how many letters, okay, are in my name. Well, that's just a scalar, okay? It's just I'm simply counting the number of letters. I can be counting something else. Now, acceleration, okay, on the other hand, so this one is a vector. So acceleration within here, it's, are you speeding up? Are you slowing down? But also in what particular direction you might be doing that in. And that does matter, right? So acceleration is actually a vector. Now we talked about speed and velocity, and you can go through these. Area, for example, so how much surface area? Well, that's simply a scalar. Okay, volume, right, which is a three-dimensional measure, again, simply a scalar. Density, right? So as you'll be maybe studying this and you may remember it from physics or you will study it in the future, okay, it's also just simply a scalar. And now there are many others, and some of them you may know, may not know. That just depends on how much studying you go. If you go very deep into physics, you're going to start learning about scalars and vectors and then what they have. But the concept and the difference between it, scalars don't talk about any direction, while vectors do talk about a direction. So for instance, something like force, right? If you're going to be exerting a certain amount of force, it will have a magnitude, but it will also have a direction that you have. For example, force like weight. So if you're measuring your weight is actually with respect to gravity pulling you down. So it's a force. So it does have a direction down. It's kind of towards the center of the earth. It's pulling you down. Okay, so and it is dependent on the mass that you have, and then the gravity. Okay, on Earth, it's 9.8 meters per second squared, or approximately around there. And it is down, so weight actually becomes now a vector. Now, learning these, will take you a little bit of time. But in this introduction, I hope what you notice is that, all right, scalars are just measurements without a direction. And that could be for any quantity. While vectors, is a measurement of some quantity, but now you do have a direction. And, we start utilizing these little hats, on top of it, a hat, or I shouldn't say a hat, but a little bit of an arrow, to utilize and let the reader know, this is a vector, that you want to talk about. So now that's a little bit of a longer discussion, with respect to this, but I think it's worthwhile because it brings you back to quantities, things that you are going to be either studying in the future, or things that you've already kind of seen, and it now illustrates to you the key difference between scalars and vectors. In one word, direction. One has it, one does not. Now, so I have talked about, in terms of the notation within here, so I've mentioned that we do have and we do associate vectors, in various forms. So we have this particular notation, in here. Now, if you're going to be drawing these notations, so if I would kind of go back down here and I wanted to, now geometric means that there's some kind of a reference. So maybe the reference is a Cartesian plane. So I'm going to just draw a Cartesian plane in here that you have. And now let's say I have a vector. It doesn't really matter where it goes. Let's say it starts from the origin, and then it's moving in this direction. So within here, now what you would have is, so you would have, let's say this is your starting point A, and then this is your ending point B. And if you wanted to designate this, you would have said one designation could be A, B. So this is your start, this is your end, and then you put your little arrow right on top to designate what you actually have, and that arrow on top just simply lets you know that this is now a vector. And now this particular vector you can certainly measure, so you would have some particular distance. So from this to here, we can certainly measure what that distance will be, or what we call it is, because distance you might designate with some kind of a distance, like in meters or centimeters or inches or something like that. But it doesn't have to be. So we, instead of saying distance, we would say, what is the magnitude in here? So that would have been the magnitude. That's what we would call that, in terms of, how long is it? Because it could be a force, for example. It could be speed, or it could be something else, So in terms of that magnitude. And now it also will have a direction associated with it. And that direction, as you can see visually, you can clearly see that there is a direction. I can take this, right? I can duplicate it. Now I can move it all the way around, and I can, shift it over here, or I can swing it back, let's say move it like this, where the magnitude might be the same, but the direction is not. So they wouldn't be the same vectors, right? So it's not just the magnitude that has to be the same, or magnitude, which is from points A to point B, but we have to think about, is the direction also the same? And if they are the same, then they would be equivalent, for example, vectors, something that, we'll talk about in just a little bit, but now you're getting introduced to this. So that's one notation, right, from one point to another. Another notation, instead of actually, providing starting points and end points, someone might just say, well, I just want to call this vector maybe V. And then, so that entire V, instead of having A and B, then you don't know really, the starting and ending, right, in terms of points. But you can say V, and then you put a little arrow over it, and that could have been another notation that you have. Now, if you want to make it specific, maybe you're talking about a force. So instead of V, maybe this was a force, and you would have done this. And then this force would have had a certain magnitude, I don't know, maybe 9 newtons. And then it would have a certain particular direction. And that direction is now going to be, how do we represent these directions, right? So this is now, what do I put in here in terms of a direction to identify it? Because the magnitude component, people are familiar with that, right? If you say 10 meters, okay, 10 meters. But now, how are we going to be specifying the directions? You can certainly say, you know, you're going north, you're going east, and that's one way of doing it in terms of bearings, right? In terms of true kind of bearings, okay, with respect to north. But there's other ways to do that. Now, as soon as we associate either a Cartesian plane, right? So the XY axes, for example, or we start talking about north and, you know, south and so on. So we put an actual planar, right? So this is just a plane in 2 dimensions. Then we do typically refer to these as geometric vectors, because now geometry matters and we can now actually associate an origin and start plotting these vectors through. So this is pretty interesting, but it still, okay, leaves a question mark in how do we designate these. All right, so before we talk about, okay, the direction, now I've talked quite a bit about magnitude in here. So I mentioned magnitude in numerous cases. Now there is one way of actually specifying the magnitude, and it is with the absolute value brackets. So if you remember, you know, the absolute values, which are just straight lines, they just are simply interested in the magnitude. Okay, so there's no sign or anything like that. And the way that we would do that is, and we say magnitude because we do not know what quantity we might be working with. So for instance, if we did have, let's say if it was 9 newtons, and then maybe, you know, this was in the direction of north, and this, you know, we would have called F, okay, and that's the actual vector. So it has this, okay, component and the actual direction. And now if you specify that you are interested in the magnitude, so you put it in absolute values, now this is just going to be simply 9 newtons. And that is, okay, in scalars. So the magnitude is a scalar where you're just interested in the value itself and you want to remove the direction entirely. So that's what this would be. And this is pretty interesting, okay, if we wanted to know what the magnitude is. You can certainly do that magnitude and this abbreviation, okay, with the absolute values, okay, in terms of the brackets, to find out what that magnitude will be. So now, for the direction as you're going through, there's really 3 different ways to be able to associate the directions. There's directions with the true bearing, and you're only doing everything with respect to north. So that's one way, and you actually go clockwise, okay, as you're going all the way around. And I'll show you an example. There is, okay, another one, which is with respect to the quadrant. So within here, so as you would have this, so this is the quadrant bearing, where it does also talk about north, but it has with respect to south, east, and west as well. And I'll give you a couple of examples with that. And then there's just the regular horizontal degree reference, which is something that you're very used to, especially if you've done, you know, mathematics. And obviously if you're doing this and you're talking about vectors, you have done quite a bit of math, okay, within here. So that degree reference, okay, is with respect to the basic horizontal of the Cartesian plane, and then it just swings around counterclockwise. So let's take a look, okay, at some of these, and I'm going to compare these, you know, so true bearing, and by the way, it's also sometimes called the azimuth, okay, bearing. I can just call it true bearing for the moment, and we should be able to convert between all of these. So let's kind of dive in a little bit deeper in here. So let me kind of clean this up for just a moment. And so let's say I have, okay, so I'm going to clean all of this up. And this is my north right here. All right, so now that this is a little bit cleaned up, so let us talk about kind of the, you know, the true bearing. All right, so that would be the first one. So the true bearing is with respect to north, and you're going in the clockwise direction in here, where you're just counting the number of degrees that you have. And the way that we designate this is we designate it with 3 digits, okay? So 1, 2, and 3. So for example, if I had, let's say this was my vector, okay, and let's say make it about 45 degrees, okay, within here. So this would have been 45 degrees in there. How would I designate that? I'm going to say that, this vector maybe, so this is the vector that I have, and it would be, okay, let's talk about an actual 2 meters, okay, so that is the 2 meters in terms of its length, and this would have been designated as 0, 4, 5, okay, degrees. So now we put the 0, okay, in front, then we put the 45. Now you might say, well, why the 0, okay, in there? Because when we do that, we actually are referring to the true bearing, okay, representation of this. And, if this was a little bit further, so let's say, I don't know, maybe it was, straight down. So it was somewhere within here. Let me change the color so that it kind of pops out in here. So let's say maybe it was this one. So this, if you wanted to know, and again, let's assume that it's still 2 meters, this would have been, because now you have moved all the way over here, which is 180, so that would have been 180 degrees. Now, these are the 3 digits that you would have. So really, that 0 is only going to happen up to really 100, and then afterwards, it just fills in the actual degrees. And you can continue with this, so if this was, let's say if it was all the way over here, very close, then you're still going in this direction, meaning that you still would be going right here in this direction all the way to there. Let me clean up all of this, okay, and take it out of there, just so that you can see this. So for that, you would have been going, and maybe this is around 300 and let's say 55 degrees all the way, and that would have been the direction, and that is with respect to the true bearing of, or the azimuth bearing, okay, with respect to north. So you just designate it with 3 digits, and those 3 digits, okay, are the actual degrees that maximize at 360 degrees. So they go from 0 degrees, okay, all the way through. All right. So that is one of the items. Now, the other items that we would have, okay, so the other kind of way that we can do the directions, okay, within here. So let's say, we're going to stick with the first one that we had, which was this 45 degrees. So how would you represent this if it was, okay, instead of the true bearing, it was actually the quadrant bearing? So that is, north, east, south, west, and etc. So this one is actually pretty interesting. So you would write this out. Okay, this would have been, so this is still 2 meters, but instead of writing 0.45 degrees, okay, what we do is, in the quadrant bearing, it is where you start from. So this is where you start from, right here. So you would say this is north, and you go from the starting position, 45 degrees, and now you say in which direction. Well, this is north, that means this is east. So you're moving in the east direction, right? So you would have had this. Now, you can also write exactly the same thing. Now, it probably wouldn't have been written out like this, but you can write the exact same thing in this style of quadrant bearing, thinking of it in this direction, that this could have been 2 meters, starting from the east side, 45 degrees going north. Those two are equivalent. So you're just saying where you're starting with, okay, and then you're going in that direction. Same thing for this 180. Well, if you were going in this direction, you could represent this as starting from north, you moved 180 degrees, and you went towards the east side, right? So that is one particular way of representing that direction. Now, another way of representing that 180 degrees, you can just simply say, well, I'm starting from the south, which is all the way, okay, at the bottom, and I'm going 0 degrees, right? And now you can say whichever way that you're going. So this is 0 degrees, east, west, it doesn't matter. You haven't moved at all. So that would have been that. Now this one would be very odd if you would say, this is starting from the south and then going east. Okay, probably, maybe better to write it like this, but this is the same way of representing the same direction. So it doesn't matter which way you go. Okay, so your starting point, and you're always utilizing north, east, okay, west, okay, those are the starting points, and then you proceed to find out what the equivalent is. So that is kind of the quadrant bearing that you would run into. All right, now the last one is one that you are very familiar with. There is no north, there is no south, right? So you remove these entirely, and you're just, okay, now talking about with respect to, so here, this would have been starting from your horizontal, so this is from this point right here. So that's your starting point. And as you know, your actual degrees that we did, right? So for example, if it was the unit circle, okay, if you did it in calculus or somewhere else, here you're starting in this direction and you're moving right there counterclockwise. And it's only one way to do it. And you would say if that indeed was 45 degrees, you would say this is 2 meters, okay, at 45 degrees, and you don't say north, east, or anything like it. Okay, so this would have been the horizontal reference that you would have, and you can go back and forth in between all of these. So those are the 3 different ways of representing it in the geometric world. So geometric world, because now we do have some kind of a reference to some kind of a plane, or to the directions of north, west, east, and south. So that's how we would be actually representing these. So that's what we have in here. So that's the true bearing, okay, with respect to north. Again, please remember, you utilize 3 digits, okay, within there that you have, and you can specify it. You can say it's based on a true bearing if it's, okay, unknown. So here on the quadrant bearing, now there we utilize, okay, all the directions, and then we specify in which direction we're moving. So you have a starting point, and then you move, and then you can write the final direction that you moved away from. And then the last one is the horizontal degree reference, which is just counterclockwise to your regular Cartesian plane, okay, that you would have your XY axes. So that's what you have. Now, before I forget, there is a reference that we do like to actually put, because when we draw these, it's almost like having a legend, right? So if you're thinking back of a legend, when you're going to be drawing these out, maybe you're referencing back, distances that are very long, or vectors that have a very big magnitude. And in that, you would actually put in. So let's say, within here, clearly, this particular vector that I have, that I drew in here, it's not 2 meters in actual size. So, if I had it through, then, what we would do is we can say that, okay, well, as we are, mapping these things out, you might put a little legend for yourself. Maybe this means that 1 centimeter is actually equal to 1 meter. That's what we would have. And that would have been a reference, and we put the double dots, kind of like a ratio, that 1 centimeter represents 1 meter. And then that way we scale it proportionally. So every 1 centimeter, if someone would measure it out, they would see, okay, that it would be actual 1 meter as a reference in real life. So because when we're transforming it back into paper or into digital form, we're not actually dealing with the same things, just like you're not dealing with a map, okay, and a map is not 1-to-1, right? It tells you, what scales you are actually using. So these scales and these references, okay, you do put them on the actual direction of your plane that you are drawing out. Now, lastly, okay, in order to finish this video, so here, the final things is, I think, that this, you should kind of think about these as well. So I'm going to just copy this down. Let me copy it and talk about these as kind of our last item in this introduction. So what are parallel, equivalent, and opposite vectors? Well, I hope, okay, that this all does make sense. So parallel vectors will be vectors. So if you would draw them, doesn't matter how they are. So if you have these duplicated back in here, these two vectors would be parallel. Okay, so they're going in kind of the same directions. Okay, so the direction doesn't necessarily mean that they're the direction doesn't mean that it matters as much. Okay, what matters is that they would never intersect. All right, so if you have these, and if you're thinking back of relations, you might think about slopes, right? So if you're thinking about slopes, then you're thinking, well, I guess their slopes are equivalent, right? So that they would actually never intersect. They're going to be parallel to each other, and that means that they're kind of at either 0 degrees or 180 degrees, okay, with respect to themselves. So if it's in the same direction, okay, then one kind of falls on top of each other. Okay, one falls on top of the other one, and that way, you can certainly take. I'm going to remove this for just a moment. If I take this, okay, and I drop it on top, right? So they are parallel, they're right on top of each other. If they're in the same direction, if they're in the opposite direction, they're still on top of each other. Now, they don't have to be on top of each other right off, but if you drop them on top of each other, okay, they would have 0 degrees between them, right? But as soon as I kind of change the direction a little bit, if I tried to take this and drop it on top of this, notice that it would just create 1 point of intersection, right? So this is kind of thinking back, even if you're thinking about slopes and lines. So if they're right on top of each other, they have an infinite number of intersecting points because they're dropped right on top. But as soon as the direction is different, right, then, okay, they are certainly not parallel. So those are parallel vectors. Equivalent vectors. So for equivalent vectors, what that means is if we take one vector, let's say v1, and then we take another vector v2, what happens is that number one, okay, from these vectors, their magnitudes are going to be equal to each other. So that is, let's say this is 2. So they have the same magnitude, but they also have the same direction that they are moving along with. Those are equivalent vectors. Now, it doesn't mean that their starting point is the same. Now, what I mean by that is if you would draw, say if I'm going to draw an xy plane to illustrate this. Let's say I have one vector, okay, like this. So this one is, okay, so this is one vector. And maybe it's going in this direction. And now my second vector, I'm going to duplicate it. This one, okay, is going to be, it's exactly the same magnitude, it's exactly the same direction. Now, the location is not the same, right? The starting points are different, the ending points right here are different if we would drop them on a plane, but they are equivalent in terms of magnitude and direction, in which way that we would go. So what that would mean is if I take this Cartesian plane and I move it over here and I move it over here, they would have exactly the same direction and magnitude, okay, if that plane would change. That's what equivalent vectors would be. Now, equivalent vectors are also parallel to each other, right? But parallel vectors do not necessarily mean that they're equivalent, because they can be parallel, right? But this one can be bigger, for example. So the direction is the same, for instance, but the magnitude is not, but they're still parallel to each other. And then the last one, okay, opposite vectors. So here for this term, opposite, what that means is they are parallel to each other. They are equivalent in magnitude, but they are going in different directions, in opposite directions. So the key thing is for here, so opposite means that their magnitudes are the same, but their direction is opposite. So the direction is opposite, right? So if you were be drawing it out, so if you take this one, for instance, okay, and I would duplicate this right here. Let me just do that. So I'm going to duplicate it, but, okay, so this one and this one, they are parallel, but if the direction is completely opposite, so if I put the arrow in the opposite way, these are called opposite vectors. All right. So there you have it. That's the introduction to vectors through various quantities that you would see in here, that you're going to be running into. And it gives you numerous ways of being able to show the actual directions. So true bearing, quadrant bearing, right? And then with respect to the horizontal. And then we should know the difference between scalars and vectors. Okay, thanks for watching. We'll see you in a future video. Bye, everybody. Happy studying and welcome to vectors and physics, I guess. Okay? See you soon. Bye-bye.